Next-generation quantum technologies, like highly precise sensors and secure communication networks, rely on entangled quantum states. Creating these requires particles of light, or photons, to exist in a superposition of multiple modes simultaneously. To create these states in a laboratory, physicists must manually design complex optical matrices. This requires calculating the exact placement and interaction of lasers, beam splitters, and probabilistic photon pair sources. Because the mathematics of quantum interference defy human intuition, researchers rely on artificial intelligence and algorithmic optimization to search for valid hardware configurations. Traditional AI approaches produce a single, isolated physical blueprint. These algorithms search for and solve exactly one specific target, like an entangled state of 4 particles. This chart shows the computational cost of finding single blueprints as system size grows. The x-axis represents system size, n, and the y-axis measures compute in aflops. As the target state scales up to include more particles, the possible hardware combinations increase combinatorially. Designing an experimental setup for a highly entangled system of just 14 particles eventually becomes computationally intractable for current supercomputers. Traditional optimization provides isolated answers without revealing any underlying physical principles. This creates a computational wall that stops progress as experiments grow in scale. To bypass the scaling bottleneck, researchers introduced a framework called meta-design. Instead of training an AI to draw a single physical setup for one state, the team trained a model to generate a meta-solution. A meta-solution is human-readable Python code that contains general construction rules for an entire class of quantum states. By incorporating logical structures like a for loop, a single script can define the underlying physics for a system of any scale. Executing this piece of code allows the researcher to input any desired system size, whether n equals 1, 2, or 8, and receive the correct experimental blueprint for that specific number of particles. Shifting the AI's output from physical components to symbolic code identifies construction rules that solve the scaling problem. Rule-based code allows for immediate extrapolation to system sizes that would otherwise require new optimization cycles. Training a language model to write physics code requires a massive dataset, linking known quantum states to their correct Python scripts. The researchers faced a significant challenge. Calculating the correct script from a target state is the exact computational bottleneck they intended to avoid. To build the dataset, they exploited a mathematical property called asymmetric computational cost. Consider basic calculus. Finding an integral, the hidden rule, is highly complex. However, finding a derivative follows rigid, computationally simple steps. Working backwards from a complex state to find the code is the difficult direction. The opposite direction is computationally trivial. A machine can randomly generate a valid Python script, execute that code to build a virtual hardware setup, and simulate the resulting quantum state. This mathematical loophole allowed the researchers to generate infinite training data by moving in the easy direction, avoiding the hard physics problem entirely. The team built a massive pipeline to generate 56 million random Python scripts containing the system size variable n. They executed each script 3 times, generating physical setups for the first 3 system sizes, n equals 0, 1, and 2. This visual details how physical setups are simulated. The hardware configurations of photon sources and detectors collapse mathematically into the specific superposition states listed at the bottom. The 3 resulting quantum states are then grouped together to form a single input sequence. The team successfully built a perfectly labeled dataset of 56 million samples. Each sample paired a sequence of 3 physical states with the exact root code that generated them. With the data generated, they trained a 133 million parameter sequence-to-sequence transformer model. While this architecture is traditionally used for language translation, here it translates physical states into Python code. The training objective required the model to take the sequence of the first 3 quantum states and predict the tokens of the corresponding Python script. This process trained the model entirely in reverse, forcing it to learn the computationally hard direction from the state back to the code. By predicting the structural syntax that produces these specific states, the AI identifies the recurring logic behind successful quantum experimental design. During the inference phase, The researchers tested the AI by feeding it the first 3 states of 20 distinct target classes. For well-known quantum classes like the GHC and W states, the model successfully rediscovered the exact human-designed metasolutions. This chart plots fidelity. 1.0 is a perfect match, shown by the top green line. Success lies in the extrapolation zone on the right. Trained only up to size 2, the model perfectly maintains a 1.0 fidelity as it scales up to size 7. The model inferred universal physical rules, extrapolating to system sizes it had never seen. While rediscovering old physics proves the model works, the ultimate goal was genuine scientific discovery. Out of 20 target classes tested, 16 had no known human metasolution prior to this experiment. The model discovered solutions for several of these, including the general spin 1/2 state and the Majumdar-Ghosh state from condensed matter physics. Generating blueprints for these states solves a major hardware challenge, but the utility of these results hinges on the format of the AI's output. Because the output is a standard Python script, physicists can read the exact logic the AI used to build the system. The code reveals a clear physical pattern, specific hardware building blocks repeating in exact mathematical intervals as the system size scales up. Human researchers can now study this generated code to extract previously unknown generalizations about quantum mechanics. Shifting the AI's target from isolated blueprints to symbolic language literally breaks the black box of algorithmic optimization, providing a direct, interpretable path for human discovery.